We're now going to learn how to configure ROMs to run the shallow water model or the barotropic model. So once again, this is the home directory here. So I'm going to go into the ROMs source directory, and this is this is the directory structure in there. We're going to go in the application directory first. If we go in the application directory, we find again that there's the Coriolis example that consists of the Coriolis compile code and this Coriolis CPP-Def file. Now I've already created the equivalent for the shallow 2D simulation, which is the shallow water model. But let's see how we can do that. So let's start all over again, and let's first copy, for example, the Coriolis into a new file, which we'll call shallow 2D underscore cppdefs.h. And so this is going to be our new cppdefs, and now we're going to go in and edit it. So I copied that, then I'm going to edit this file. Okay, and as we go here, then we're going to have to do a couple of things. First, it's no longer Coriolis, but the application is going to be shallow 2D. Okay, so I'm going to change this over here and over here. Okay, oops, sorry. We're going to call this shallow 2D. Very good. The next thing is we go in the model physics. Now in the model physics, we're not going to have the three-dimensional equation, so we're going to undefine this option. Okay. Then we go in the computational grid and initial condition. Now in this case, both the grid and initial condition are provided by us, by the user, so we're going to undefine these options. Now, and also this one over here. Now, undefining the options I could do is equivalent of just deleting these guys. I could do this. This would be the equivalent. So, but for now, just for the instructional purpose, let's just leave them as undefined. Then in terms of the surface boundary condition, we still have a surface momentum flux boundary condition because U and V velocities have a momentum surface boundary condition. But the ST flux, which is the surface tracer flux, we don't have these any longer, since this is just two-dimensional. So we're going to undefine, we're going to undefine the surface tracer fluxes. Now for the bottom boundary condition, we still have U and V drag coefficients, which is the drag at the bottom, but we don't have a bottom boundary condition for the tracers, BT flux. So we're going to undefine this stuff. Okay. Now in terms of the lateral boundary condition, we're actually going to have walls everywhere, so we don't have periodic boundary condition. So we're going to undefine these as well. Okay, and let me tell you that when there is no explicit definition of the lateral boundary condition, the default is just a wall at the boundary. Now okay, so let's just leave it at that for now. Now there's some additional options that I want to perform here. We're not going to have floats this time. However, we are going to enable something called averages. Now averages is an option that allows, let's actually look what it is. I'm going to save that. And if you go in this directory, you have a README file. And if you search for averages, what this averages option does here, just alone, is define if writing out time average data. Now the reason why we want to write out this time also time average data is the fact that because we have two types of waves that we're going to be looking at. Ones are the initial gravity waves, which are very fast waves, and then the other ones are Rossby topographic waves, which are more slowly moving. We want to basically, in order to see the slow evolution of the fields, we want to time average to filter out this fast inertial gravity wave. So we're going to have two types of output. One is the typical output, which is the history file of the model, and that one we will use to look at the transient adjustment process, where it has the radiation of all these inertial gravity waves. And then we're also going to have an averaged output file of the fields, which we will use to look at the slow moving component of the flow field evolution. Okay, so that's just as an indication. So we've done now we finished preparing the CPP-Def file. Okay, so the next thing is to define this new grid. As you remember, we have to define the parameters of the grid inside the code, and this is by adding the file models mod param param.f. This is where we define the dimensions of the grid. Okay. Now, what are the dimensions of the grid? Well, let's go back in our MATLAB in our directory here in the ROMs examples directory in shallow 2D. We go in MATLib. Okay, we run MATLAB. We load our grid. Okay, and now we look at the dimensions GRD all LM and GRD.mm. Okay, so these are the dimensions in the I direction and J direction. So it's 198 by 58 points. Okay, so now that I know that, I can go back to this file here. Oops, sorry. I don't want to CD. I want to open this file. Okay, I will search for Coriolis. Okay, and now I can copy the section of Coriolis per se into another section, which I've already done, and call this section shallow 2D. Okay, so I already copied, and then we can modify this section by introducing the LM parameter, which as I said is 198, and the MM parameter, which is 58, and I'm going to leave the number of vertical layers to 20. Now another thing that I'm going to change is NAT, which is the number of active tracers, and this is 0 because we don't have neither temperature neither salinity. Okay, so that's one thing. The other thing that we have to configure is the boundary condition, the analytical one, and that again is done in the file nonlinear analytical. This is the same analytical.f, which is the same thing we did for the Coriolis example. So we go there, and in this case I already made some edits, and the things that we have to take care is basically the surface boundary condition for the momentum. So this is the SUSTR, which is surface U stress, and the wind amplitude in this case is going to be 0 because we don't want to look at the forced solution but just at the adjustment from the initial condition. So this is for the U component, and there's going to be another one for the V component. So we've set now the surface boundary condition, and that's about all we need to do in this analytical file, because the initial condition is no longer analytical, but it's provided as an external file, and this is different from the Coriolis example. Okay, so we can close that. Once we have done that, we can log in on the master to compile the code. So let's put the password here. Okay, so we go in ROMs SRC. We go in applications. Okay, and here you have again the compile script, which is very similar. It's the same as the Coriolis, except that you change a couple of names. For example, up here in the place where the user defines its variable, we're going to say the executable file is going to be stored in ROMs example directory shallow 2D in the bin folder, and it's going to be called shallow 2D in capital letters, which is this application -ROMs. Okay, and we're also going to tell here the initialize this variable that says that the cppdef file for this application is shallow 2D underscore cppdefs. With that in mind, we can close this, and then we can just run the compile script and just wait. And if you're lucky, these things is going to work well. Now keep in mind that sometimes when you compile, you may get an error associated with this mpif file already exists. Sometimes it happens and the code just stops compiling. When that happens, try to compile it again, because this is a bug in the compiler. So just give it another shot before thinking that you've done something wrong. Okay, so it compiled well, and it put so now we find that the code is actually in this directory here, and we can do an ls of that, and indeed we have our executable. So this is all for setting up the shallow 2D case in ROMs.